Today's subject is geologic time. Understanding the time of the events, geologic features, and structures and processes is extremely important for being able to build the history of our Earth. Rocks record geologic and evolutionary changes throughout Earth's history, and they actually help us to understand the timescales of different processes happening. And without the time perspective, all these events, all these geological processes and events will not have much meaning to us. So in this case, the time scale gets really important. And we have actually two different types of understanding of time. First, the one we use in our daily lives, numerical dates, to and which specify the number of years that have passed since an event occurred. When we are talking about the numerical dates, we are talking about real big numbers in the context of geology. For example, we can easily say for a limestone, it being 250 million years old. But it is not always very easy to talk about the exact numerical dates or numerical ages of geological features or processes. And in those cases, we mostly use relative dates. And by using relative dates, we put things in a sequence of formation. So we can say a Hermit shale is older than Coconino sandstone. In this way, we actually can put things into an order, into a time order, and then we talked about things happening relative to each other. For creating a time scale, we use several principles. These principles now may seem quite trivial or easy for you. However, in their first time recognitions, they were real big and important things for geology. So there are six really important principles. First of them is superposition. Then we have original horizontality and lateral continuity. Also cross-cutting relationships. And we have two separate geological features or events that we call as inclusions and unconformities that we use for identifying the time. First, let's talk about superposition. Superposition actually starts with an assumption and says that in an undeformed sequence of sedimentary rocks, each bed is older than the one above and younger than the one below. So in this case, when we are talking about different sedimentary layers, we like to accept the lowest one or the one at the most bottom part will be the oldest one. And then when we move upward through the sequence, we will go younger and younger and younger, and very top layer is going to be the youngest one. We also apply this principle to the surface features like lava flow and ash, the beds of ash. So for extrusive igneous events from volcanoes, we can use these and identify which layer of lava or ash would be younger than the other. The second principle called original horizontality. So this principle actually assumes that all the layers, all the sedimentary layers will be deposited in a horizontal position. So if they are still horizontal, that means they have not been disturbed. Or if they are curved or change their shape, anything other than being horizontal, like in this picture, that means they actually went through some tectonic events and they have been disturbed. Another principle for relative dating is lateral continuity. So for this principle, we assume that all the sedimentary layers are going to be continuous in all directions until they end up with other feature or thin out or grade into a different sediment type. So as you see here in this picture, we have these horizontal sedimentary layers on top of each other. So by using the earlier principles, we can say this layer at the very bottom is the oldest one, and this yellowish color looking layer on top is the youngest one. In this case, there is still water on top and sedimentation process is going on. But again, by looking at these layers, using the other principle about being horizontal, we can say that these layers aren't being disturbed. But when we go over here and check the second part, we see that there's a canyon, likely dug by a river. And on both sides of this canyon, we actually have the same layers continuing. So these features are going to be explained by lateral continuity principle of relative dating. So we can just say, by looking at the both sides of a canyon, we can just say this layer on the right side of the canyon and this layer on the left side of the canyon are going to be equal or same age or deposited at the same time before they got cut through by this river and formed the canyon. Another principle about relative dating is cross-cutting relationships. So we say that any kind of cross-cutting features are going to be younger than the actual depositional environment. So here we see a fold, and we see that fold actually change the horizontality of the other sedimentary layers. So we know that this fold is younger than the sedimentary processes happening in this area because it actually cut through them and change their horizontality. Or here, in this case of these dikes, we have this likely limestone material cut through by these dikes. And this material was here when the dikes started to push their way through it. So we can say the dikes are going to be younger than the surrounding geological material. There are also inclusions. Inclusions are fragments of one rock unit that are enclosed within another rock unit. So in this case, when we look at this picture, we see that there's an igneous intrusion coming in. And we all know that this igneous intrusion, when it's moving upwards through these rock layers, will actually bake the area around it and also take some crumbles, some pieces of the host rock into that. And when we look at these pictures and see these features in here, we can say that, okay, this igneous intrusion is younger than the surrounding material because it actually took pieces of the surrounding host rock into itself. However, when we look at the one layer above, here we see the particles, the pieces from this igneous intrusion, and also particles from this host layer, host material, up in the next sedimentary layer. That means the sedimentary layer on top is younger than whatever staying down in here. So so we can say the rock containing the inclusion is going to be the younger one, like in this case, the igneous intrusion containing the inclusion from this green pictured rock, or this browny sedimentary layer containing the inclusion from this green and orange looking rocks. We also have unconformities that we use for relative dating. So we call layers of rock that have been deposited without interruption, so being completely horizontal, called conformable layers. And an unconformity is actually the structure breaking in the rock record, and it is going to be produced by non-deposition and or erosion of rock units. We have three basic types of unconformities. First of them is angular, and then we have nonconformity and disconformity. Again, we all use these three different types of unconformities by starting with the assumption of horizontally deposited sedimentary layers. So here in this picture, you see an example of angular unconformity. This picture actually shows these almost vertical sandstone layers cut by this angular unconformity. And then above here, there are other horizontal or gently dipping sedimentary layers. So how it actually occurs. At the beginning, we have all horizontal, real nice and quiet sedimentary layers. And then uplift happens. Then we use this water on top, the sedimentation process stops, and uplift actually creates this exposed material up in here, which will be open to being eroded. And then erosion takes place. While this material being eroded, it is going to turn back into a flat surface. However, we already have these angular layers created by the uplift. And after the erosion is done, we may have another set of sedimentary layers coming on top of this eroded surface. And we actually call this boundary in between next set of horizontal layers and the first set of sedimentary layers being angled by the uplift as angular unconformity. So as you can understand it from its name, those sedimentary layers laying underneath an angular unconformity should have angles or dipping angles other than being flat or horizontal. And then the second type of unconformity is disconformity. In this case, we again will have some older horizontal sedimentary layers, but in this case, we will not have them being angled. So they still will stay horizontal, but something will happen. The, the deposition process will pause for a while, and maybe we will get some erosion. And later, the deposition process will start from where it was left and then keep accumulating more and more but younger horizontal sedimentary rocks. In this case, it is quite hard to actually distinguish these conformities since they mostly horizontal on the top and below layers of this boundary. However, we can understand it from the existence of time gaps between these sedimentary layers. And the third and the last type of unconformity is nonconformity. In this case, at the bottom of this unconformity boundary, we have igneous material, not sedimentary materials. And when we have this kind of a boundary between igneous or metamorphic rocks and younger sedimentary layers, we call this boundary as nonconformity boundary. We actually can see all these three types of unconformities in the Grand Canyon. So let's just look at this picture and identify them. So at the very bottom, we have this granite and some schist. So we have some intrusive igneous rocks and we have some metamorphic rocks. And then we know that when we have this igneous or metamorphic material, and some sedimentary material on top, the boundary in between them will be called as nonconformity. So this boundary is going to be called as nonconformity, and this boundary. And later, we have some of previously horizontally deposited sedimentary layers formed some angled layers. So they got affected by either a plate tectonics event or some sort of deformation. So they are now angled. And what we know when we have this angled material and above that we have this horizontal sedimentary layers, the unconformity between those two will be called as angular unconformity because below this boundary we have angled sedimentary layers, above this boundary we have horizontal sedimentary layers. And when we move upward, between these horizontal sedimentary layers and another set of horizontal sedimentary layers, we have another disconformity. And we call this, because both layers are horizontal, we call this specifically as disconformity. And above here, we have another disconformity. But we know that the material in here, red wall limestone, is going to be different than the material in here. So that actually tells us that there is some pause in time during these two depositional features or some changes in the environment that they were being deposited. So how we apply this relative dating principles? Now let's just look at an example. Here we have a series of sedimentary layers beneath ocean. So we have layers A, B, C, and E. We know that the A is going to be the oldest layer, E is going to be the youngest layer. And we also know that since they are horizontal, they weren't disturbed by any other deformation or plate tectonics event. And later we have this igneous material in here. It's a sill. So it actually like the dike example in the previous slide, it actually came later than these layers. So it is the youngest in between these layers A, B, C, and E. And then we have a dike. So we know that the dike is actually cutting through the sill, so a dike must be younger than the sill. Now it is the youngest thing in this block. And something happens, and all this material becomes tilted. Now all these layers are angled. They aren't horizontal anymore. So we know that there was some sort of a deformation happened. And after a while, we got some erosion, and we had this boundary of angular unconformity. And above that, we again have another sedimentary environment formed, and layers of sedimentary material came on top of all those previous materials, and they are all horizontal. So in this case, we know that the layer K will be the youngest. And we actually can put all these layers and features into a time scale, and relatively we can say which one is younger than which one.